All right. So energy diagrams. We talked about some of these energy diagrams yesterday, where we talked about how they looked. We're also going to be introducing this equation as well, just kind of introducing it, where we have the heat of the products that are summed together, added together, minus the heat of the reactants when they're added together is going to equal our overall reaction. We kind of talked about that yesterday, how if we have stuff that's getting produced and we're bringing those bonds back together, that's going to give off energy. This is going to require energy. So if the heat exits, the products are at a lower energy. That's because energy has been released. Endothermic, the opposite happens. And this was that diagram that we talked about yesterday. And I introduced to you yesterday also the concept of what this activation energy is, which is the energy of where the reactants start out with. They have to overcome that reaction, that activation energy. And in certain cases, they don't, and the reaction just doesn't occur. In other cases, we have a spark or we have something else that happens that gets that over that hump, and then the reaction can proceed. So this is what those exothermic reactions look like. This is what the endothermic reactions look like. The difference between where the reactants start and the products end then is what this delta H is that they had up in your equation at the beginning. So this energy here from here to here is going to be your delta H. The same here. All right. So the difference in the energy, again, we can use that as these, and this would be 15.8 for you guys. I don't think we're even doing 15.8, are we? If you look at the front of the packet, I don't know how far we're going with this. So we're never going to get to the mathy of this. I just want you to know that that is called delta H, and this is how you would calculate it. Okay. You need to know that if it's negative, it's exothermic. If it's positive, it's going to be endothermic. Delta H then is labeled as the difference between those products and reactants. And then we talked about activation energy. And I think we do get into 5-6 before we leave. So here's a small activation energy. Here would be something with a large activation energy. Okay. Something with small activation energy, you're going to have a lot of heat. The delta H is going to be great. And exothermic, if it has a large activation energy, you're not going to have much heat given off here. That activation energy, what it does is it is used to break bonds. So activation energy is going to break bonds, or it might overcome intermolecular forces. That's the other thing that it could possibly do. Energy is going to be released from the reaction. It comes from those new bonds forming. If the energy released, if there's more released, then it's exothermic. So more energy released, you've got exothermic. If more energy is required, then you're going to have endothermic. We have something called catalysts. You may have heard of catalysts. In your mouth, in your saliva, you actually have one called amylase. That is a catalyst. It's an enzyme in there, and it aids in breaking down sugars, complex sugars like starches. So if you take like a cracker, for example, and you chew, don't swallow it. You got to just keep chewing it for like a minute or two. Eventually that cracker will start to taste sweet, because the amylase in your saliva will start to break down the starch, which is a complex, it's a polysaccharide. It'll break it down into a simple sugar like sucrose or glucose. And that glucose and sucrose have a sweet taste to it. Starch doesn't. Starch has kind of bland. But amylase will break that down into those simple sugars, and then you'll get this sweet taste in your mouth. So go home and chew on a saltine tonight and see if that doesn't happen. It's kind of a neat kind of experience if you didn't do it in biology. I always used to have the kids do it in biology, but that was the old bio curriculum, so who knows. So these catalysts are going to lower that activation energy. So it takes the activation energy down so that a reaction can occur where it normally might not. These catalysts are not going to change how much energy is produced or required in the end. Okay, so the delta H isn't going to change here. It's just going to get it over the hump to get it to this process. Also, the catalysts are not used up. So they can go back in and be used again and again and again. So I liken this to going to Madison. Okay. I could walk to Madison, right? How long would it take me? Really long time, right? Okay, but I could do it. Might take me a good day, but I could get there by foot. Might have some blisters, but I could do it. There's a faster way to get to Madison. By car, right. Is that car used up by the time I get there? Could I make trips to Madison every day using that car? So it's getting me there faster, right? And it's not used up. Now, I know there's a little bit of gas there. We're not going to talk about that. That's kind of, it is what it is. But you get the idea behind a catalyst. It makes the reaction happen sometimes faster and sometimes just at all. Because sometimes this activation energy is so high that without that catalyst, it wouldn't happen. And if you're going on to take AP Bio, they talk a lot about catalysts in there, a lot about enzymes. And understanding this mechanism and this concept behind this makes you a better biology student. Okay? Also make you a better chem student. We'll get to that. All right, so we want to draw a reaction pathway diagram for this reaction. We're going to label the products, the reactants, and the delta H. So I'm going to start out here. This axis is going to be potential energy. Why do they label the y-axis or the x-axis on those? Course of reaction is what they call it. Remember, reaction can be abbreviated RXN. All right, when we look at this, our delta H is negative. So does that mean that my products are going to have more energy or less energy than my reactants?
Yeah, ask that question again. Sorry.
This is a negative delta H. Will the products have more energy or less energy than the reactants? Less. Okay. So my reactants are going to start out over here. Every reaction is going to have some activation energy. And then we want to go down here to our products. Okay. We are going to then put some labels on these. These are my reactants. These are my products. Between here and here is my activation energy. Okay. And then I'm going to change colors one more time here. Let's do blue. Between here and here, this I'm going to call what? Delta H. And what value am I going to give it? Negative 1196 kilojoules per mole. Reaction. You may not understand some of this. You were gone yesterday. I'm sorry. I can talk you through it if I can. I got a couple people going, so just wait a second. Okay, she's here. All right. What did you want to ask me?
Nothing.
Are you sure? Okay. All right.
I'll ask questions after Bill.
Okay. All right. Does this make sense? Everything on my labels here? Did I do everything that they asked us to? I think I did. Okay. Good. All right. So let's move on here. We're going to do the next one. Draw the reaction pathway here on the diagram. The reactants are starting at 40. So my reactants are going to start here. My delta H is going to be negative 15. So if this is a negative 15, this is going to go from 40 to what? 25. So 25 is right here. So that's where my products are going to end. The product's energy then, 50 minus, so it's going to be 25, and that's going to be kilojoules per mole. I am going to draw in this. These are my reactants. I'm going to have an activation energy here. And it doesn't matter how much you put in for your, if they don't give you a value for your activation energy, you can make that hump as high as you want it, okay? And then I need to go back and I need to, EA for the reverse reaction would be what? So the EA for this one was 50. So for the reverse reaction, it will be negative 50. Wait a minute, EA, that's activation energy. They did give us a value for that. Hold on, back the train up. Okay, so 40 plus 50 is 90.
I dropped it off.
Oh, thank you.
Yeah.
So that's going to be 90. Bad Lippy, didn't read the instructions. All right, so my activation energy is going to be 50 kilojoules per mole. This value for my delta H is going to be 25 kilojoules per mole. And that would equal my delta H. That's a delta, believe it or not. Delta. This is my EA. E sub A. All right, the activation energy for the reverse reaction. Let's skip that one. We're not going to do anything with that in here. I don't want to get into that with you guys. Okay, so then this guy for a catalyst. Catalyst means that you are going to lower the activation energy. They didn't tell us, that I can see anyway, what that lowered to. So I'm just going to do a dotted line here, and that's going to be my new reaction. It's just lowering that activation energy. Okay? Questions on that guy? All right. Heat transfer. We talked a little bit about this yesterday. We talked about heat transfer and heat coming in from hotter particles to colder. Okay, it travels. Heat is what is going to be transferred. We call that thermal equilibrium. Okay. So molecules that are at a lower temperature, more of them are going to be moving slower. So that would be the negative 100 here. The 220 is the one that's in the middle, and then the blue one would be 600. So when you have something at a given temperature, that temperature is the average temperature for whatever material, whatever temperature you're at. You will have some molecules that might be slightly slower, some slightly faster, but this is the overall average of it. When two things are brought together, that heat is going to get transferred from the hotter item to the smaller one, and it can do that in 3 different ways. It could do it as conduction, where it's touching, convection, where you're using like air to move it, or it could be radiation, which can happen through a vacuum, which is why the sun's energy gets to us. Right? So 50 grams of aluminum is placed in 100 grams of water, and that water is at 25 degrees Celsius. The aluminum was 85. So what's going to happen to the temperature of the aluminum? The aluminum is at 85. It's put in 25 degree water. What's going to happen to the temperature of that aluminum?
I think it's going to be low. It's going to get lower.
Right. It's going to decrease. Good. The average kinetic energy is also going to decrease, and the average speed of the aluminum will decrease. Okay. This is pretty much the same thing as that was. You can watch the video on this if you want, but if you click on this QR code, remember that'll bring up a video for you. But but it's pretty much the same idea. So, all right. Any questions about heat transfer, thermal transfer? Okay. I got the quizzes ready. They are over here. They never got put into a folder. Remember, today is the last day to turn in your yellow sheet if you want credit for that. Your green lab technically is due today, but I'm giving you till Monday on it for the last day to turn it in. And then I'm not sure if I'm going to do a quiz tomorrow yet or not, but be ready for one just in case on those 3 sections. You're not taking this.
No. But I need to take the titration for that.
Okay, give me a minute to get this up.
I asked you one question before that though.
Uh-huh.
I'll wait at your desk.
Okay.
How was I supposed to get the concentration of the acid?
So you M1V1 equals M2V2. So this is the base molarity and volume. This is the acid. So you just need to solve for M acid, the molarity of the acid.
That's it?
Yeah.
Okay. I wasn't overthinking it.
Really? That never happens out of you. So that M1V1 equals M2V2 is the only equation that you're going to need for this quiz.
Okay.
If you can't remember that, you have a brain freeze and you need to talk to me about it, come back and get it for me.
Okay.
Okay.